Hello, today I will show an example of the Rao-Cramer lower bound in a particular probability density function that we have here. But first I want to show that I am following this book, Introduction to Mathematical Statistics for Hogg, McKean and Craig. Okay? So they defined the lower bound here as the minimum value that can have the variance of the estimation of the maximum likelihood. So basically here we have the assumption that this estimator is unbiased estimator, as is shown here. It means that the expected value of that estimator will be exactly the statistic, the value that we are looking for. Okay, the variable that we are looking for. So now what? Also they mentioned about the concept here about the efficiency, which basically the estimator that we call it efficient when the variance is exactly this number, the lower bound, the cream lower bound. So when it is in exactly the same number in this moment, we call it that this is an efficient estimator, which is what they define it here in this part. Okay, so I found this example, this number, the 623, a good example to see how they become asymptotical to a normal distribution at the end of the example. So let's start here. So they define the probability density function. This is something that we get in advance of the estimator. Theta is equal to 1 p1 plus x minus theta squared. Okay, and they also define that it will go from minus infinity to infinity, the range of x. Same thing for theta. Go right. We have here. So what do we have to do? Basically, we have to verify. This is the question. If our lower bound Cramer Rho, this one is equal to n, right? This is basically the first question that we have. And the second question, if they is asymptotically if the maximum likelihood estimator minus this, it will be asymptotical to normal distribution 0 to 2, right? So this will be the second part, this is the first part. For that, let's start with the first part. We know that the Fisher information, right? Fisher information is the second it is the place. Let's say we have this function here, right? Basically this part will be the maximum likelihood in this case that we have. So the point where there is a maximum, the second derivative will be negative, so this is why we have the negative here, and the expected value of the second derivative of the log function of this f and x theta with respect to theta will be the Fisher information. This is one thing. The other part could be the second movement of the function, which is log theta, and this will be a square. I don't have a space here. So we can try this or this one. Let's see which one maybe is better for us. We don't know yet. We have to get the derivative of this. So first, the log of the function theta basically will be this log of pi 1 x, right, which is equal log 1, which is 0, right, minus log pi minus log, this is using the log properties, okay, log 1 plus x minus theta square, and this is 0. Then we calculate the derivative of this log pi minus log 1 minus, sorry, plus x minus 0 square, right, this is a constant 0, and basically it will be, this will go like this 2, so this is exponent will go in this place, multiplying the internal 1 square. Okay, so this is the first derivative that we have of the function applied log. We don't care for this log, this is a one-to-one function, so it is sometimes make it easy to do the calculation, but it should be fine. So the second derivative for this one x 0 it looks kind of messy because it's this part first, right, plus x minus is square plus the derivative of this, which is minus 2 minus this part, right, and the derivative of this minus 2 x minus theta, again I don't have a space, plus the square of this, which is 1 plus x minus theta square. This is very messy to do the calculation with the integral. So if we have to do the second derivative, because basically this is the second derivative of the log of the function theta, right? The second derivative. This is too messy. So in this case, I would recommend to use the Fisher information that have the second moment of the first derivative to the square. Log x theta, right, to the square. So let's do it. Oh, you guys don't see it. I don't remember. Okay. This is messy, so I would recommend to use just the first derivative in the second moment of the expected value of this function, which is the Fisher information. Okay, so for that, let's write it again. Which is the expected value of the derivative, the log of the function, right, squared, which basically is the expected value to the square. Okay, so what do we have here? We have that the expected value of this is equal to the integration from minus infinity to infinity to x 1 plus x minus theta to square squared, right, multiplied by the original function, right? What is the original function? Remember, it is pi 1 plus x minus theta squared dot dx. Looks kind of horrible at the beginning, but we can apply substitution. Remember, in the integration in calculus 2, we have the substitution, so I can say that x minus theta will be the tangent of u. Okay, we know also that tangent basically will be infinity, something for tangent of minus pi or 2 minus infinity. So if we got the derivative of this, we can say that dx, right, basically this is the second square of u du. Okay, so now doing the substitution, we can move this and this outside. We have 2 pi integrating from minus pi over 2, which is this one, right? The u to pi 2 . So we have here, this is squared and this is u, basically the tangent of u squared, and we have also the dx which is this. So we have tangent of u secant squared of u du, and in the bottom we have 1 plus tangent square, right? 1 plus tangent square of u, and this, everything here is to the square, but this is also the same thing, so it will be to the cube. Okay, we can apply trigonometrics here. Remember, this part that we have here is the secant square of u. Okay, so we can remove this, and we have still the secant square there, so it will be something like this: pi over 2 negative pi, let's put the tangent, the u squared. Now we have the secant square of u to the third and secant square of u to the u, and that is what I say, we can remove 2 from this. For this is 6, so if we remove 2 it will be 4. So pi minus pi over 2 pi over 2, then we have tangent square of u secant 4 of u. What else can we do here? I will say we can convert this tangent to sines and cosines. Minus pi over 2, right? So we have sin here, u cosine u1 sin 4 of u du. Then if we apply, we put this over this, we can basically remove these 2 and 2 from here. I will have 2 over pi over 2. I will have sin 2 of u cosine 2 of u by du, and equal, if we apply a trigonometric identity here, we know that this is sin 2 of 2u, right? sine of 2u, right? How can we solve this? Actually, I think we can use the other trigonometric identity, that we can say this is 1 minus sin 4u over 2, this one, right? You can put it there, and then we will have so this will go away with this one. Let's put it in. One over pi two for u. We can still apply another substitution here. Very simple substitution. Let's say for u. So the m for the u. We can have, so this part can go directly, right? But this part will need the substitution. Sorry, I didn't show it what we are doing here. We have to apply this for everywhere, so we have to put it, because it's the u will go away here, so basically the m and still this will be u minus pi we have to update this part. To pi because we are working around with the cosine. 1/4 cosine m. And this will be minus 2 pi 2. This is the first part, minus this other part that we have. Yeah, but I don't have a space. Space here, so it will be 2 pi. Let's put it again. Over 2 minus pi. That's again 2 pi multiplied by 2/4. that we have here sin m less sin m again from 2 pi to pi basically if we do this calculation this will be 2 pi multiplied by pi. This can go away, right? And all this basically is 0. So I will say that the Fisher information of theta in this case is 1, 2. And the lower bound Rao-Cramer is 1 and the Fisher information of theta, right? So in this case will be 1 over 2, which is 2n. Now we have the first part of the question, remember, but from here we can very easy say that there is the theorem the theorem 6.2.2. It says that we can have our estimator to the actual theta will asymptotically become the normal distributed, right, 1 over the Fisher information. Let's write it here. 1 over the Fisher information. Okay. So in this particular case, we have that the Fisher information is 1 over 2. So we will have in this case that the lower bound, the inverse of the Fisher information is Fisher information. It is 1 over 2. Basically, it is 2. So by this theorem, we will say that whenever n increase infinitely, it will tend to be the normal distributed in with the variance 2. Okay, I hope you guys like it, the exercise.